situation. But in any case, so the internet has been like buzzing in and out, but we have like a backup hotspot. So if for some reason I disappear, just so everyone knows what happened to me. Okay, so my talk is about perverse sheaves and regular Hessenberg varieties, and this is joint work with Peter. And because the time is relatively short, I'm not going to say that much about perverse sheaves, and instead I'm going to try to like give a motivating introduction to Hessenberg varieties and explain what people are interested in and what we were interested in and what we managed to do. And then maybe like for technical details, we can discuss more in the breakout rooms. So throughout this talk, G will be a connected, simply connected, semi-simple algebraic group over the complex numbers. And fractor G will be its Lie algebra. And if you like, you can just as well think that G is SLN. And for the rest of today, I'll fix a Borel subgroup B along with its Lie algebra. And again, if you like SLN, you can imagine that B is just the subgroup of upper triangular matrices and then Bion matrices of non-vanishing determinant, of determinant 1. Okay, so a subspace of the Lie algebra G is called a Hessenberg subspace if it satisfies two conditions. So it has to be a B submodule and it has to contain the Borel. So what this means for us is that, well, there are simple examples like all standard parabolics. Say, standard. But in general, H is not required to be a subalgebra. So I could have, for example, the subspace of SL3 where I include the Borel and the negative simple root spaces. And in the lower left-hand corner, I just put a 0. And this is going to be one of the examples that we talk about. Okay. So when I fix a Hessenberg subspace like this, I have an associated bundle over the flag variety. And this bundle has a natural Poisson structure, which I'll explain very briefly. So on the cotangent bundle of the group, we have a left action and a right action of G. And this restricts to what I'll consider to be the right action of the Borel B, which I've written over here. So this is a Hamiltonian action. And it comes equipped with a moment map that goes to the dual of the Lie algebra of B. And under the killing form, I can identify this dual with G mod the nil radical. So this is under the killing form. And also I can identify the cotangent bundle of G with the group cross the Lie algebra. So here I trivialize with respect to the left action, and then I identify G star with G. And then this moment map is going to factor through just the projection onto the second factor. So now you can see that this associated Hessenberg bundle is actually just what I get when I take the pre-image under the moment map of H mod n, and then I quotient out by the B action. So the symplectic leaves, concretely, the symplectic leaves of the sky are in one-to-one correspondence with symplectic reductions at B orbits. In this quotient H mod n. Okay, so this vector bundle keeps left action of the group G, and this action is Hamiltonian for this Poisson structure, and it also inherits this second moment map that just takes a pair of a group element and some x and h to what happens when I apply the group element to x. So by dot, I mean the adjoint action in this talk. And then the Hessenberg varieties associated to this bundle are just the fibers of this moment map. So explicitly, I can say that they are cosets G times B, where when I apply G inverse to X, I land in the Hessenberg space H. And the sort of extremely broad goal is to understand their geometry. But as I'll try to motivate this as, like I said, extremely broad, and their geometry can be very, very complicated and mysterious. Okay, so first example, the simplest example where H is just equal to the Borel. And then we get a familiar object, which is the Grothendieck-Springer simultaneous resolution. So this is like the Springer resolution, but for the entire Lie algebra. And the fiber above a point X is the Springer fiber, so just a collection of Borel subalgebras that contain that point X. So these, when X is regular, this fiber is finite, but when X is non-regular, it can become sort of very, very complicated and difficult to understand. Okay, and now before we go on to the second example, I also want to state some general properties. The first one, I think, so Hessenberg varieties have been studied in a large variety of contexts, and they've received a lot of attention, in particular in type A, because they're related to many combinatorial things. So in this talk, I attribute certain results to certain people, but it's often the case that these results were sort of known, at least in special cases, before they were written down. So my goal is to give just a reliable reference for the most general version of these facts that I know. So the first thing we'll need is as a result on the dimension of these things. And thus, in its greatest generality is due to Kriga. And it says that if we have a regular element in the Lie algebra, so by this R, I mean regular. And by regular, I mean that the dimension of the centralizer of X is equal to the rank of the Lie algebra G. So in particular, regular elements don't have to be semi-simple. They can be nilpotent, or they can be anything in between. Then the dimension of the Hessenberg variety associated to X is equal to the dimension of the Hessenberg space mod B. So this is, if you look back at this vector bundle, the total dimension of the space is the dimension of the group plus the dimension of H mod B. And this moment map is surjective. So this is the dimension that you would expect the generic fiber to have. But this result tells you more. It tells you that all regular fibers have this dimension. Okay, and then the second result, which is due to Demari, Perchesi, and Scheiman, who are actually the first ones, I believe, to study Hessenberg varieties in the late 80s or the early 90s, says that for a regular semi-simple element, so here, regular semi-simple, is what the superscript means. For regular semi-simple element, the associated Hessenberg variety is always smooth. And when I restrict this family to the regular semi-simple locus, I get a locally trivial fibration. So all of these regular semi-simple fibers are isomorphic to one another. So with these two facts in mind, we'll look at the next example. I'll let delta be the set of simple roots, and then H naught, which is sometimes called the standard Hessenberg space, will be the one I gave as an example at the beginning, which is the space of consisting of the Borel plus all of the negative simple root spaces. So this means, again, in SL3, I take upper triangular things and I add exactly what is immediately below the diagonal. So property 1 tells us that the dimension of the fiber above a regular element for this H naught is equal to the rank. And this is equal to the dimension of the centralizer of this regular element. So of course, since these Hessenberg varieties are fibers of a G-equivariant map, we always have an action of the centralizer GX on the Hessenberg variety associated to X. And one can prove that in the case of this Hessenberg space, this action has an open dense orbit. So in fact, we can think of Hessenberg varieties for the standard space H naught as being sort of compactifications of centralizers of regular elements. Okay, so continuing with this example, we have two special cases. If S is a regular and semisimple element, then its centralizer is maximal torus. And this maximal torus acts on the corresponding Hessenberg variety, which is smooth with an open dense orbit. So this means that this Hessenberg variety is a toric variety, and toric varieties are indexed combinatorially by fans. So the one corresponding to this one is the fan that is made by the Weyl chambers. So in SL3, this is going to look something like this. And this was maybe the motivating example that led Demari, Pertesi, and Scheiman to define these objects in the first place. Okay, and then at the other extreme, we have regular nilpotent elements. And a regular nilpotent Hessenberg variety for the standard space is something called the Peterson variety. And this is something that was introduced by Dale Peterson in the 90s in different contexts. So he wasn't interested in any of the Hessenberg setting, but they've turned out to be very useful in representation theory. So for example, they're the tool that's used to compute quantum cohomology of flag varieties. And thus, it doesn't really matter what the Peterson variety is, but I want to give it as an example because it's a fairly singular variety. So in sufficiently high rank, it's not normal. And this sort of illustrates for us that even above regular elements, the corresponding Hessenberg varieties will become singular and can have sort of a complicated geometry. Okay. So one more remark before I get to what we did. Because I required the Hessenberg space to always contain B, I always have this G-equivariant inclusion of the growth and Dieck-Springer resolution into the Hessenberg family. And this commutes with the moment maps. And this gives me an inclusion of the growth and Dieck-Springer fiber into the corresponding Hessenberg variety for any space H. And this inclusion is equivariant with respect to the centralizer action. So in particular, if X is a regular element, then you'll remember that X is contained in a given Borel if and only if its centralizer is contained in the corresponding Borel subgroup. And this is if and only if the centralizer fixes this Borel in the flag variety. So what this means is that in the regular case, we can recognize the Springer fiber inside the Hessenberg fiber as the set of centralizer fixed points. So in the boundary of each of these Hessenberg families, you have this growth in Dieck-Springer resolution, and you can describe it very explicitly. And if you want to understand it in terms of Poisson geometry, you can show that this is the sort of stratum of this variety that is the union of all of the closed symplectic leaves. So the Hessenberg family is stratified by symplectic leaves, and the ones of minimal dimension are going to be closed, and they're going to exactly form this growth in Dieck-Springer subfamily. Okay, so let me pause for a second and ask if there are any quick questions or clarifications, and encourage people to sort of chime in.
Why did you say this was a union of closed symplectic leaves?
I didn't explain this. So if you look back to over here where I described the Poisson structure on this family, I think, is this Travis? Cool.
Yeah, yes. Sorry.
If you look back here, you see that I remarked that the symplectic leaves in this family they just come from symplectic reductions of b orbits in this quotient, h mod n. So you can identify which of these b orbits are closed, and then you can take their reductions, and those will give you the closed symplectic leaves, and in fact, they're going to be exactly the ones that make up the Grothendieck-Springer resolution. Okay, so moving on. So now I'll fix a regular semisimple element in the Lie algebra, and let T be its centralizer, which is a maximal torus. And then this has a Weyl group associated to it, which is just normalizer of T mod T. And it's a sort of relatively well-known fact that the Hessenberg variety corresponding to S, equipped with the action of this maximal torus, is what's called a GKM variety. So GKM stands for Goretzky, Kottwitz, McPherson, and in this case, what this variety needs to satisfy is that there are finitely many fixed points under the T action and finitely many one-dimensional orbits. In general, GKM varieties are defined for non-smooth things, and then you also require something called equivariant formality, which is a more technical condition. But because this Hessenberg variety is always smooth, we don't care about that aspect. And then this GKM property implies some things about the cohomology of these varieties. So I'm looking at T-equivariant cohomology. With complex coefficients, and I always have, by pullback, a map from T-equivariant cohomology of the Hessenberg variety to T-equivariant cohomology of its fixed points under the T action. And if my variety is GKM, then this is an embedding. And on the other hand, I always have the specialization map P from T-equivariant cohomology to ordinary singular cohomology. And the GKM property implies that this map P is surjective. So the observation that was made by, is there a question? Not. The observation that was made by Tymoczko is that one can define sort of in a natural combinatorial way. Okay, one can define in a combinatorial way an action of the Weyl group on the equivariant cohomology of this Grothendieck-Springer fiber that is made up of the T fixed points on the Hessenberg variety. And Tymoczko showed that it restricts through I
Отсюда мы тоже выйдем.
Weyl group action on the T-equivariant cohomology of the Hessenberg variety, and then it descends through P to a Weyl group action on the singular cohomology of this variety. And this has come to be called the Tymoczko dot action. And then, I'm a bit short on time, so maybe I'll try to be less wordy. So fundamental question is what does this action look like, and which irreducible representations of the Weyl group appear in it. And this is, well, the answer to this question is known entirely in type A, where it becomes a question about representations of the symmetric group, but in other types it's sort of completely unknown at this point. And this is what we tried to answer. And the way that we approached this was using an observation that was due to Brosnan and Chow in type A, which is that when we take the regular semisimple part of this Hessenberg family, which, like I said before, is a locally trivial fibration, we have this natural action of the monodromy, which is just the fundamental group of the base, on the cohomology of the fiber. And what Brosnan and Chow observed is that this action factors through the Tymoczko dot action. So this action by Tymoczko, even though its definition has no relationship to this, actually has a very geometric interpretation. And then this lets us apply the tools of Springer theory to try to describe which W representations appear in this cohomology ring. So this is, I'm going to skip over the right-hand side of this slide, and maybe talk more about perverse sheaves generally in the breakout room. But the bottom line is that we want to give some impression of which Weyl group representations appear in this cohomology ring by using the Springer correspondence, which is a correspondence that identifies irreducible representations of the Weyl group with what are called nilpotent orbital complexes. So to every irreducible representation of W, I assign a nilpotent orbit O and an irreducible representation of the component group of the associated centralizer. And in the special case where G is SLN, this becomes an actual bijection between irreducible representations of the symmetric group and nilpotent orbits in SLN. And this bijection is the one that everyone is familiar with, in which both of these things are indexed by partitions of the integer n. So, first result says the following: this Hessenberg space has an annihilator under the killing form, and so for example, the annihilator of B is n. And because I required H to contain B, this means that this annihilator is contained in N, so all of its elements are nilpotent. And our first theorem is that if an irreducible representation of the Weyl group appears in the action of the Weyl group on the cohomology of this Hessenberg variety, then this nilpotent orbit intersects H perp in some element. So H perp contains some nilpotent element that belongs to this orbit. And concretely, in the case of SLN, what this means is that if I have a representation of the symmetric group indexed by some partition that appears in this action, then the annihilator H perp contains a nilpotent element whose Jordan type corresponds to the conjugate of that partition. So this is a pretty explicit criterion, and after we posted the paper, we learned from Martha Prekup that it's also possible to prove the converse by using some identifications that have been made between this Tomochko dot action and type A and various combinatorial objects in some things called chromatic quasi-symmetric function, but this is something that I'm not very knowledgeable about.
Anna, can I just interrupt quickly? So you're saying that this theorem, the converse, is also true in the case of SLN? Is that what you're saying?
Yes. Yes. So in the general case, this doesn't really have this theorem. It's not clear how one would formulate converse and how one would prove it, but in type A, because the Springer correspondence is an explicit bijection, it's straightforward to say this. But I don't think this converse is written down anywhere. Like I said, it's pretty far outside the scope of our paper, the kinds of methods that people would need to use to show it. Okay, so I think I'm going to stop here. I was going to say a little bit more about the singular cohomology of these guys, but I'm already out of time. So yes, so thank you. I have a thank you slide.